So here's an interesting question on kinematics. So what we have is a slender bar that's called AB, and end A of the bar is attached to a drum that's rotating counterclockwise via a string, right? So as the drum is rotating, it's also pulling end A of the bar towards it, so to the left, basically. And the question is asking us to find the angular velocity of the bar, right? Because what's happening is that as end A is being pulled to the left, um, the bar will rotate and it will also translate in some fashion because it's also leaning on this corner here. Okay, so let's see how we would approach this. What I would normally do is I would draw the free body diagram. Okay, so I would draw the bar, and well, actually in this case it's a kinematics question, so having a free body diagram with all the forces is not very useful. So we have to think a bit what we can add on this drawing here. So what we have is a rolling drum, and we know that the point on the top of the drum, so this point here, we know what speed and we know what velocity that has. Namely, the speed is acting, or the velocity actually is acting to the left, and the value of that is omega 0 r. Okay, so the speed is omega 0 r, but the velocity of that point is minus omega 0 r times I, right? Because I is the unit vector in the x direction, minus because it's going to the left, and that's the velocity. Now, here's the thing. This is the velocity of the drum at its highest point. But this is also the velocity of the string, right? Because the string is attached to the drum, but the string is also inextensible. So if the string is inextensible, in a way it's moving as a rigid body, right? So what I mean by that is each point on the string has the same velocity, omega 0 r, pointing towards the left. Because if, let's say, if this point is omega 0 r one way and this point is something different, then that would mean the string would stretch, but that's not actually what's happening. So if each point on the string has the same velocity, it means point A also has the same velocity, omega 0 r, right? Because point A is attached to the string, so the string gives point A the same velocity, omega 0 r. Okay, so what I'll do now is I'll draw this here. Okay, so this is omega 0 r, and what I'll also write is that the velocity at point A is minus omega 0 r times I. Okay, now you might have noticed that we haven't really specified our coordinate system, but we'll do that now. So our coordinate system is looking like this. So we have x, y, and of course z would be coming out of the screen. And what we have to do now is, using this information, we have to figure out how to find the angular velocity of the bar. Okay, so how do we do this? Well, first of all, let's take this coordinate system and let's stick it in point A. So I'm going to come up with a coordinate system which is attached to the bar and it's rotating with it, and I'm just going to draw the x and y axis because it's going to simplify the drawing a bit. And now we're trying to figure out how can we use this to find the angular velocity of the bar. Now, to do this, we're going to call this point here, let's say P, right? So point P has a special property, which is it's leaning against the corner, and as a result, it doesn't actually, its velocity is such that it cannot actually go into the corner or detach or fly away from the corner, right? Which means that if I just, this one here, which means that the velocity of point P has to be in uh, either this direction or this direction, right? So the point here is that the velocity of point P has to be purely along the bar. It cannot have any component perpendicular to the bar, either this way or that way, because if it's pointing into the corner, it means it's going, you have two solid objects going into each other, which is not possible. And if it's doing this, it means it's flying away from the corner, which again, it's not the case. So we're going to use this to figure out the angular velocity of the bar. Okay, and here's how we do this. First of all, uh, we don't really know this angle here, but it's okay because we know something else. We know a couple of other things. Namely, we know this distance that we call x. So this is the distance from the horizontal distance from point P to point A. So this is x. That's what we're given. And we're also given this height, right? So we're given the height from point P all the way down to point A. Just like that. Okay, so that's h. So if we know if we're given x and h, we can actually find the tangent of theta, right? So we have tan theta is equal to opposite over adjacent, so that would be h divided by x. Okay. So with this in mind, let's try to now apply Euler's equations to find the velocity of point P. Okay, and we'll take it from there. So we have the following. So the velocity of point P, and actually let me take this with me. So the velocity of point P is going to be equal to the velocity of point A plus, and then we have the angular velocity of the bar. Remember, it's not the angular velocity of the drum that we know, right? It's the unknown angular velocity that we have to find. And then cross product with AP. That's the vectorial distance from point A to point P, right? So let's actually get an expression for the velocity of point P. So the velocity of point P is, and then we have minus omega naught r times I, okay? That's VA, that's what we did in the first part of the question, and then plus, and then we've got I, J, and K. Now, I don't actually know. I can sort of guess which way omega is acting, but I'm not going to do this. I'm going to assume that omega is positive. So I'm going to put it here with a plus, and it only has a k component because it's a 2D problem. So in that case, AP has an x and a y component. So the x component is minus x, actually, because P is to the left of A, and then H is positive, and then this is 0. Okay, so if we solve this determinant, then we can find out what the velocity of point P is. Okay, so this is, let's see, minus omega naught r times I plus I times, and this is going to be minus omega h, and the j component, the y component, is going to be minus omega x. Okay, and I'm going to write this on here. So we have the velocity of point P as, and here's what I'll do. I'll group the terms together. So I'll put all the i's and the j's together. So the velocity of point P is going to be equal to I times minus omega naught r minus omega h minus omega h. And then for the j component, we have minus j, or actually let me write this, plus j times minus omega x. Okay, so that's the velocity of point P, and this is the x component of it, and this is the y component. Okay, and this is going to be relevant in a bit, because what we're going to do now is we're going to use the fact that the velocity of point P can only have a component parallel to the bar. Okay, in other words, the component of the velocity of p perpendicular to the bar is 0. Okay, and that's what we're going to use. Now, let me try to draw this here. So we've got the bar, and I'm going to sort of just zoom in on point P. So point P is going to be somewhere here like this. Uh, There we go. So this is point P. And I'm going to say that the velocity in the x direction that we just calculated, I'm not going to mind the fact that we've got minus signs in the equation above. Instead, I'll say, okay, in general, if the velocity in the x direction is positive, and if the y direction velocity is also positive, then how do we actually calculate this normal component of the velocity? Okay, so the way we would do that is we would look at this angle here, that's theta, and we get the following. We get Vn is equal to Vx, and then we've got Vs sine theta, right? Because this Vx component has a component along the normal direction, which is this blue line, right? And that's the sine of theta. And then Vy has a component in the normal direction. And you can actually see that this angle is also theta. So that's going to be plus Vy cosine of theta. Okay? And this is also equal to 0. Okay, so what this gives us is Vx sine theta plus Vy cos theta is equal to 0. And if we actually divide by cosine theta, we get Vx and then sine theta over cosine theta plus Vy is equal to 0. Now, the reason I did that is because this here is now equal to tan theta that we already have an expression for. So if I rewrite that here, I have that Vx and then tan theta plus Vy is equal to 0. Okay, so Vx, I can now substitute what Vx actually is, which is what we found here. So that's minus omega naught r, and then we've got minus omega h, like that. Now tan theta is this h over x expression. So that's times h over x plus, and then Vy is minus omega x. Minus omega x, and that's equal to 0. Okay, and from here we can easily find out what omega is, because this is one equation with one unknown, right? This is the only thing we don't know, is this omega. So let's actually try to solve it by putting all the omegas on one side. So I'm going to leave the minus omega r here. So this is going to be times h over x, which means that everything goes to the right. So on the right, I'm going to have omega h squared over x plus omega x. In other words, if I factorize omega, that's going to be x plus h squared over x, like that. Okay, so minus omega 0r h over x is going to be equal to omega, and then I can bring this to the same denominator just to get one fraction. So that's x squared plus h squared over x. Okay, as you may notice, now we can cancel out the x's in the denominators, giving us an omega of minus omega naught, and then we have rh over x squared plus h squared, and that's the final result. So this gives us an expression for omega in terms of everything else that we know, which is omega 0, which is the angular velocity of the drum, the radius of the drum. So we have omega naught, we have r, we have h, which is the height of of this point here, and we also have x, okay? And the minus in front, we're using a right-handed coordinate system, right? So the minus in front actually tells us that the bar is rotating clockwise, because clockwise is negative, right? And that's actually what's happening, because as you think about it, as point A is moving to the left, the bar is actually rotating clockwise, right? It has, you can sort of visualize it, that as A goes that way, B goes something like that, and the bar is going to rotate clockwise as a result, and the minus here that we got is consistent with that. Okay, so yeah, that's the end of the question.